You're sitting in an aircraft in stronger turbulence. The cabin is shaking. You're feeling all these bumps. At Turbulence Solutions, we develop technology so you just don't feel the turbulence anymore, also known as turbulence canceling. The vision is to make flights turbulence-free, the whole aviation industry turbulence-free. I'm Andras, Galffy, CEO and founder of Turbulence Solutions, did my PhD research on flight control, turbulence flight control, and also I'm a pilot myself, flying since more than 10 years. For me personally, I don't have a problem with turbulence. I don't have a problem with G-forces. Actually, all the opposite. I really enjoy doing aerobatics, doing loopings, positive G, zero G, negative G. But I know a lot of my friends, a lot of passengers who really do not enjoy turbulence, and they are even afraid of flying because of turbulence. So this is something special about flying. It's really polarizing. On the one side, you have this really positive, really passionate bunch of people like me. On the other side, you have this rather scared, afraid, ashamed of flying people. So just to give you some rough feeling where I'm right very up there. And if I am troubled in my life, if I'm stressed out, if my company is going to break up and the whole world is going to break up. To stay focused, to calm down, I ask myself 3 questions. First, will I die because of that? Usually not. Second, is my family endangered? Usually not. Third, will I still be able to fly? So for me, flying is really a life existence item. Unfortunately, there are a lot of people, it's rather like flying could kill me, flying could kill my family, so don't fly, take the train. And also, flying kills the climate, the whole planet, the whole society, flight shaming. So I want to focus on that fear of flying and flight shaming, and especially I have my personal goal for my life to help to overcome unnecessary fear of flying and unnecessary flight shaming. So to put that into perspective, just extreme positions. Fear of flying, if you never build an aircraft and you're building your own aircraft, and if you never flew an aircraft and you try to fly your own built aircraft, that's a famous last flight. You will very probably die because of that, and you shouldn't do that, and it's good that you're afraid of this operation. If you're just flying an airline flight today, it's very, very safe. It's much safer than if you are driving a car slightly drunk or driving a car doing some text message, some WhatsApping. That's, I would say, 1,000 times riskier than just taking an aircraft as a passenger today. On the other side, flight shame. One very extreme position would be jet setting every weekend going from New York to Dubai just because of shopping. Okay, very obviously, I think you could be ashamed of that. It's just egoistic. It's not the resources for the whole society, but just for you. If you go on the other side, you're taking one transatlantic flight and could be even a business jet, I think that would be justified for this case, to sign a peace contract to end war, very extreme position, I think that would be justified, right? So everybody would agree. So to get away from positions, flying is good, flying is bad, flying is safe, flying is unsafe, I want to go to interests, and the interest behind flying is mobility. So on one side you have mobility, on the other side you have the input, and that's energy. How much energy needs to be put in by batteries, needs to put in for an eVTOL, needs to put in for ground mobility with the car we had. But in my context, it's turbulence for air mobility. So to empower you to just do your own judgment, is it justified? How much energy is in this mobility? There's a very simple physical equation that's just true because it's a basic principle. Mobility energy equals force times distance. Simple example, you're driving in a car, 100 kilometers, you need 6 liters. If you're driving 200 kilometers, you need 12 liters. 300 kilometers, 18 liters. So the more distance for the same force, for the same operation, the higher you get. If you have a lighter car, we just had this, it's 3 liters or equivalent energy, electrical energy. So that would be keeping the distance. I want to go 100 kilometers, reducing the force. If you go slower, reducing the force, 4 liters for 100 kilometers. If you go faster, and that can be justified, maybe you have a patient who needs to have medical care, then you will go with 150 kilometers per hour, having 8 liters for 100 kilometers. So now there is a very basic misconception about flight shaming, because flight shaming should be rather be long distance travel shaming. Only flying is the most convenient way to go transatlantic. You wouldn't go in a ship for 3 weeks. But if you go 10,000 kilometers, you just need 100 times 100 kilometers. So this is a long travel. And it would mean also for a car, instead of 6 liters, 600 liters. I put it a little bit more specific and now in variables, so it's shorter. Let's go into a very specific thing about the force. So the force is now here with mg, so gravitational acceleration, m is the mass, and eta, that's like the efficiency. The smaller eta, the better. Reducing the mass just reduces your force. We just had it, the LUV, the light vehicle. The same for aircraft. The lighter the aircraft, the less energy you use. And especially for aircraft, it's a problem that a lot of 6-seater, 8-seater aircrafts are only flown with 1 or 2 persons. So these are rather the luxury business jets, 2 persons in there, just flying the big aircraft, mostly for comfort reasons. So this is exactly what we can tackle. If you don't say, oh, this is a small aircraft, you still fly with it because it's the more economic and the better way of flying. The eta, just to give you also a broad, you can use it for all the mobility. So if you're a river, you're very, very efficient. For 1 meter of altitude, you get 10 kilometers of flowing somewhere, getting from A to B. So Vienna is at 150 meters approximately, and the Danube until the Black Sea goes like 1,500 kilometers. So that's really efficient, 1 to 10,000. If you have a glider, if you have a very good bicycle, if you have skiing, some wheel, it's 1 to 100. That's also pretty good. Just 1% of gravity you need to overcome all the time to get to your mobility. What do we have with flying? For a good, economic, efficient aircraft, it's 1 to 20 approximately. The same for a car. So this is, again, a misconception, a specific example for you. If I want to go from Vienna to Madrid, it's rather hard by train. We have a very good system in Europe, and still it's hard by train. You can now have the conception flying is bad. What would be the solution? Driving by car. So driving by car, you would be 22 hours in the car going from Vienna to Madrid. If you want just 1 person, you would be all alone, 6 liters per 100 kilometers. An aircraft uses about 3 liters per 100 kilometers per passenger if it's fully loaded. So it's way more efficient to fly. And it's the way better option for you. You have some mobility need. You have more time where you want to go. It's even more justification, more output of your mobility. So just to give you some rough framework that also complies with our basic purpose of making flights turbulence-free, it's reducing emissions. And this now brings me to turbulence impact. So now relating this to the actual turbulence case in aviation. Climate and aviation share a common space. It's the atmosphere. So there is interaction between climate and aviation. Climate leads to turbulence, and this is even increasing, not just because of aviation emission, but because of a lot of emissions. But we have climate warming, that's a fact, and we get stronger winds, stronger turbulence. So we get even more flight turbulence. But also without climate warming, we would have flight turbulence. Aviation needs to respond because we can control what we do to the system, so we won't overload the wing, it won't break because of us doing aerobatics if I don't want to do aerobatics, but turbulence can all the time overload your system. So a wing needs to be stiffer, has more mass, just to withstand the once-in-a-lifetime strongest turbulence. This means that an aircraft approximately has like 10% of extra mass only to withstand the turbulence of the air. So that means if we wouldn't have now this bidirectional relation from climate to aviation, we could reduce at least the mass and so on by 10%. For light aircraft, this is even more true. Why? Because this is the effect of not flying the small one, because that's unsafe. What does it make feel unsafe? It's not crashing, but it's just you're feeling the turbulence. You're just strongly feeling the input of the turbulence. So if you fly instead of a 2-ton aircraft, a 600-kilogram aircraft, with our equation from before, you just have 1/3 of the energy for the very same operation. It's 2 persons getting from A to B, flying, being very fast. So just having some now motivation why we took the road that we're taking, starting with some background on turbulence. One is you get insolation, so a lot of surface heating from the sun, you get rising air. And turbulence for an aircraft is just like a wave going up, going down. So rising air, falling air. The other is mechanical turbulence. That means you just have a steady wind, but the steady wind hits obstacles, you get some turbulence behind it, or also ground roughness. The more winds, also because of climate warming, the stronger the mechanical turbulence. This is interestingly very much affects the small aircraft, the light aircraft operating in a low atmosphere. Already in the 1950s, engineers started to do solutions like we do now because you were flying down there. But what happened then? The jet age started. So now we're flying in this big, big aircraft above the atmosphere, or above, not above the atmosphere, but above the troposphere, so above the weather activity. So you can compare it like we are flying in these big ships on very calm sea above the weather. And now down there are these light aircraft with very rough sea. Now consider advanced air mobility, the so-called urban canyon turbulence. Who do you think will trust this technology if 6 out of 7 flights are really bumpy? So that won't be mobility for the first time. It will be a really showstopper for this, but we have a solution. It's turbulence canceling, and this is now what I'm going to introduce. So on my left, you see like a really bumpy ride, adding plus minus 1 G in stronger turbulence. This is the light aircraft in low atmosphere, that's actual dynamics. So double the body weight pushed into the seat and 0 G. On my right side, this is suppressed by more than 80% by active control. So this is more mathematical, where you can see, I just turn around. So this is really this plus minus 1 G, and activating the system reduced by more than 80%. Nice vision, also realized in an actual 2-seater aircraft. This is such a 600 kilogram very light aircraft, a lot of turbulence impact, but what we have is small flaplets. So like the winglet on the wing, we have flaplets put into the flap, easy to retrofit, and these are like birds do with feathers, just compensating the turbulence. They are by purpose or in purposeful, very limited, very small, because so the effect is limited, and also for certification reasons, it's much easier to get it into actual flight operation. The basic principle you can see here, you are measuring in front of the wing what turbulence hits the wing, so you have differential pressure. This differential pressure is the same effect that happens instants later on the wing, just in a big scale. The whole wing integrates this differential pressure to force. And then we have our flap deflection, where you can see again, it's on purpose, just small deflections, just this limited authority that we have in the system compensating the turbulence. So we have this path of starting with small aircraft. On one side, it's just the need of the market, because now light aircraft get much more interesting. These innovative ones, especially also advanced air mobility. On the other side, it's just the only way to get to the more complex things, to the more safety critical things. So the second framework I want to introduce, it's very easy. The complexity for our system is size times authority times criticality. So aircraft size, we start with a 2-seater. We could go up to the airliner with 500 plus seats. That's also a lot of mass. It's a flying weapon at the end. Now we have a very limited weapon that could impact somewhere, but an A380, maybe future A390, that's a real weapon flying. We just know how to deal with it. Authority. If we raise our small flaps to really full deflection of all surfaces, it's just much more critical. 737 MCAS was a full deflection of a trim of an elevator, pitching the whole aircraft down into the ground. We don't start with that. We want to have very limited impact, just doing the small corrections. And criticality, is it just a comfort feature, an assistance system like we start with? So you can deactivate it at all time. If some check fails, okay, it's deactivated. You have 1 turbulent flight out of 100, that's okay. Or is it the reason why you put mass out of the wings and the structural stiffness decreased? Because you guarantee the function. So that's a completely different story. And you see it's like a multiplication. So we are at the moment at 2 times 2 times 2 equaling 8 out of 1,000. If you have 10 times 10 times 10. And also some very fast way of saying there's also a 0. If you multiply with 0, it gets down to 0. So 0 size would be a paper plane. Doesn't matter what you do with that. It's just some grams. 0 authority would be just a feather on an A380, no effect at all. And 0 criticality would be an aircraft on ground. You could have a very sophisticated setup. If it's not flying, it's not safety critical. Okay, so this brings me to our current state. You've seen it flying in a video, in a test flight video. End of the year, you can already have it installed in your system. So you can order it now if you have a Shark Ultralight. That's the aircraft, 600 kilogram, very efficient. This is a 2 times 2 times 2, 8 complexity. So that's how we start, and step by step go up. This is a video 7 years ago. I did it in my PhD study proposal to give some insight how it could end. And this is 10 times 10 times 10. So this is full complexity, a big airliner with all the flap deflections and guaranteeing the function so you can take off the mass and having all the flights with reduced mass and therefore reduced emissions. My prediction, a normal prediction, would be 8 times 8 times 8. So that's 512, 50% of maximum complexity 1,000 by 2035. But I was asked to be bold, so it's 10x, 10x, 10 by 2035. Make flights turbulence free.